now have a lot of experience with certain kinds of functions. We've learned all about linear functions, quadratic functions, polynomial functions, rational functions. In this chapter, we're going to introduce two more new functions, the exponential function and the log function. So today we're going to talk about the exponential function, and to introduce you to it, I'm going to have you work in groups before the lecture part today. So you're going to work through this activity about rabbit utopia, and then we'll come back together and discuss it after. So we had two rabbit models. We developed two models for the rabbit population. This first one was linear, right? And it represented a growth of 1,000 rabbits per year. And the second one you figured out we call exponential, and it represented a doubling of the rabbit population every year. So if we look at the linear model, what does this first 1,000 represent? That's the starting number of rabbits. And if we were talking like a little bit less in context of this rabbit model, what does the 1,000 and a 1,000 plus t linear model represent? Yep, that's what the 1,000 on the t represents. This 1,000 in the graph, what does it represent? Your y-intercept, your starting amount and your y-intercept are synonymous. So, yeah. So it's the starting amount of rabbits, the number of rabbits you started with. It also is your y-intercept if you graph it. All right, and the second 1,000 in the linear model, Scott just said, represents the growth rate, 1,000 rabbits per year, right? Per year. It's a slope, right? It's a slope of the line, and you interpret slope as a rate of change. All right, what about the two? Oh, sorry, I didn't finish this question up here. What does the 1,000 mean in the exponential model? It's also the starting point slash the y-intercept. So that starting point, that y-intercept, shows up in both the linear formula and the exponential formula. Okay. All right, and then what does the 2 represent in the exponential model? The doubling. Yep. It is a growth factor, right? Because the word for something you multiply by is a factor, right? So if I'm multiplying by 2, we call that 2 a growth factor, and it represents the doubling. In this case, it's doubling. It could be tripling, or you could be multiplying by 1.5 every year, right? So in this case, it's the doubling. It's a growth factor. So you graphed the exponential, you graphed the rabbit population using the exponential model. You should have gotten something that looks like this. You might have had some slight variation based on the window that you chose. And I was able to blow this up so that you can see a little bit better where it crosses the y-axis. So the y-intercept of this equation, the way you find the y-intercept of anything is you plug 0 in. 1,000 times 2 to the 0. What is 2 to the 0? 1. Anything to the 0 is 1. So this says 1,000 times 1 is 1,000. So that's our y-intercept, and you can see that on the graph. Right? Crosses at 1,000. What's the horizontal asymptote of this exponential function? What is 0? Y. Y equals 0. Yeah. So you can see as x approaches negative infinity, the graph is approaching this asymptote of y equals 0. All right, so that takes care of our introduction to exponential functions using rabbits. The definition of an exponential function is a function of the form b to the x. where you're raising a number. So b is a number like a 2 or a 5 or an 18, and x is the variable. Right, so this is different from a polynomial because a polynomial had x as the base and the number is the exponent. Now they've swapped places. But we have some restrictions on that base. It has to be positive and it can't be 1. So what would happen if I made the base 1? If I said, oh, let's think about a function that looks like 1 to the x. It wouldn't be exponential because it would be constant, right? 1 to the anything is 1. So there's nothing special about that. We've studied constant functions before. So this is not exponential, right? And then what if I made b negative? What if I went like -2 to the x? What would the graph of that thing look like? It would be all over the place. Why? It would switch from positive to negative depending on the value of x, right? When x is even, it would be positive, and when x is odd, it would be negative. So this graph would look like, right, something like that. Right, and that's not what we mean when we say exponential growth, right? Its growth should just be going up, or exponential decay is just going down. Right, so that we restrict it. Base can't be 1, base can't be negative. All right. So there are really only 2 flavors of graphs for exponential functions. Here I gave an example of each: 2 to the x and 1/2 to the x. When that base is bigger than 1, we have exponential growth. Right? And b is called the growth factor. The base is called the growth factor. When the base is between 0 and 1, a fraction, small number, then we call that exponential decay, and b, the base, is called the decay factor. All right, what do you notice about the graphs of 2 to the x and 1/2 to the x if I put them on the same set of axes? There's some symmetry. Yeah, why is one a reflection of the other over the y-axis? Reciprocal. It's not inverse because inverse are reflections over the line y equals x, not the y-axis. But if I write g of x equals 1/2 to the x, right? That's the same thing as saying 1 over 2 to the x, because I put the x on both things, 1 to the x over 2 to the x. But then 1 to the x is just 1, 2 to the x. But I can move things from the denominator to the numerator if I do what to the exponent? Switch the sign, yeah. So 1 over 2 to the x is the same thing as 2 to the negative x. So this guy is the graph of y equals 2 to the x, and this guy is y equals 2 to the negative x, which is equivalent to 1/2 to the x. So I made the x value negative, and when we talked about transformations, when you put a negative on the inside, it reflected over the y-axis. So just trying to pull in some older stuff. All right, let's come up with some general properties about the graphs of exponential functions. Because these are the only 2 basic shapes that an exponential can take, we're going to draw some conclusions just from these 2 graphs. So looking at the red graph and the black graph, what is the domain of both of those? Negative infinity to infinity. They both continue all the way to the right and all the way to the left. And what's the range of both of those graphs? 0 to infinity. They never go below the x-axis. So y values start at 0 and go up. But we don't include 0. It never actually gets there. It approaches the asymptote. Looking at these graphs individually, right? Like look at just the red graph. Is it 1 to 1? What is 1 to 1? Anybody? Yeah, its function. It is. That means its inverse is also a function. Yes. How can you tell? The vertical line test tells you it's a function. The horizontal line test tells you it's 1 to 1. So the red graph passes the horizontal line test, as does the black graph. You have to consider them separately, just they happen to be on the same set of axes, but they are their own things. So both, yes, are 1 to 1 because they pass the horizontal line test. And importantly, that means that it has an inverse that is also a function, which is what we're going to study like in a couple classes from now, the inverse of this thing. Do either of these have any extreme values, maxes or mins? Nope. And y-intercept for both of them is 1, 0, 1. And the x-intercept for either? Neither has an x-intercept. They both have the same asymptote. Where is it? Y equals 0. And here is the only place where they differ, end behavior. They've got the same, you just reverse it, right? They're the reverse end behavior from each other. So I will write them out separately. I'll do 2 to the x. Its end behavior is as x approaches infinity. 2 to the x approaches infinity, right? And as x approaches negative infinity, 2 to the x approaches what? 0. Good. And then for the 1/2 to the x, as x approaches infinity, 1/2 to the x approaches 0. It's approaching the x-axis, yep. And in the other direction, it will approach infinity. Okay, so we should be able to find an exponential function if I give you its graph. The only thing you have to figure out is the value of b. Okay, so you just have to figure out what that growth factor is. What is that constant multiplier? Like in the rabbit example, to get from 1 year to the next, you multiplied by 2. To get from 1 year, pretend this is years, to get from 1 year to the next, what do you multiply by in this example? 5. Yeah. So you can make yourself a little table, x, y, right? And put in the points that you know. I've got 0, 1 is my y-intercept. And then I have 1, 5. And then I have 2, 25. And from there, you can try to figure out what the multiplier is. You say, okay, what do you multiply to get from 1 to 5? What do you multiply by to get from 5 to 25? Times 5. So that is your base. So the equation is just y equals 5 to the x. Just got to figure out what the multiplier is, what the factor is. That's your base. Not too bad, right? Not yet. Okay, but then we also have to be able to look at transformations of exponential functions. Okay, so let's take a look at this first one. First, we'll figure out what the multiplier is with not think about transformations, right? So I'm just going to make a little xy table and put in some values I know. I've got 0, 4 is my y-intercept, and then I have 1, 5, and 2, 7, and 3, 11. That should be enough. Can I find a multiplier, right? Like, what do you multiply 4 by to make 5? 1 1/4. 1 1/4. Yeah. How can you figure that out? How did you figure that out?
Okay. So what I did is I divided 5 up, just cut them up to sections of 1.
Uh-huh.
And 5 has 5 of those sections.
Yeah.
And 4 to get to 5, it has one more than a section, which is 1, 4. It's 4. It's really hard.
That's interesting. You have a really visual way of describing that, which is awesome. And I actually do that too. Like, Yeah, you could set up a little equation and say, what do I multiply 4 by to make 5? 4x equals 5. Then you have an algebraic way to do it. Divide both sides by 4. And 5/4 is the same as 1.25. Right? So 1.25. So let's check if that multiplier continues to work. We'll do 5 times 1.25, and maybe we'll get 7. Okay, so 5 times 1.25 is 6.25. Uh-oh. Pretty sure it's 1.25. Yeah. So okay, so 5. Yeah. So the asymptote has moved, right, from a standard, right? In a typical exponential function, the asymptote's at 0, and now the asymptote's at 3, right? So I shifted up somehow. I shifted something up by how much? 3 units. So if I shift the whole thing down, right, this would go through 0, 1. This would go 1, 2, 3, 1, 2. Bring this guy down 3. And then if I can find the equation of that guy in pink, then I just have to add 3 to it, and I get the guy in black. All right, so let's look at the pink. X, Y. I've got 0, 1. Then I've got 1, 2. And then I have 2, 4. Do we have a constant multiplier? 2. Yeah. Times 2. 1 times 2 is 2. 2 times 2 is 4. So from this table, I would predict that I should have the point 3, 8. Right, so 11, this comes down to 8. So yeah, that would be on there. So the equation of the pink graph I just drew, where I just moved it down 3, is 2 to the x. Right? But then the graph in black is 2 to the x shifted up 3. So that is going to be plus 3 shifts up 3. Yeah, sure. Okay. What is 5? Where's the 5 come from?
0, 4, 1, 5, 2, 7, 2, 11.
Oh. Yeah. I see, you're doing a recursive process. Yeah, that makes sense. Yep. Yep. Yeah. Yeah. So you have to kind of guess what the what transformation has happened, and then using that guess, try to work your way back to the formula. Yeah. At 0. Yeah. For any b to the x, no matter what the base, there's always a horizontal asymptote at 0. So it is easy to identify vertical shifts. If the asymptote has moved, you've got a vertical shift. Horizontal shifts are more difficult. Yeah. Yep. Like, let's look at this next one. This could be a horizontal shift, right? Because the asymptote didn't move, right? But for b to the x, what's the y-intercept for any b to the x, no matter what the base is? 1. Yeah, no matter what my base is, if I put in a 0 for x, you get 1 as the y-intercept. So, but what's the y-intercept of this guy? 3. Okay. But did I shift up from 1 to 3? Did I do a vertical shift? How do I know this is not a shift? Yeah, the asymptote hasn't moved. So I know that this is not a vertical shift. Not a vertical shift. So I could have shifted horizontally, or what else could I have happened? Stretched. Yeah. So if my y value was at 1 and now it's at 3, what's my stretch factor? Factor of 3. Yep. So this is going to be y equals 3 times something to the x. I just have to figure out what the original multiplier was. So let's see. If I take each y value and divide it by 3, then I'll get the original unstretched function. So this is 6 divided by 3, I'll get 2. Here I have 12 divided by 3, I get 4. So here's my unstretched function. And do I have a constant multiplier here? 2. Right. So this, I went from a y value of 1 to a y value of 2 to a y value of 4, multiplying by 2 each time. So this is 3 times 2 to the x. And you can always check. If you come up with a formula and you're not sure if it's right, it's all the points on your graph have to match your equation, right? So you say, well, let's see, 2 comma 12 is on my graph. If I plug a 2 in for x, do I get 12 for y? Yeah. 1 comma 6 is on my graph. If I put in a 1 for x, do I get 6 for y? Yeah. So it definitely takes, there isn't like a this is how you figure it out when it's transformations. You have to kind of play around with what you know about transformations to try to figure out the formula. But once you have a candidate, it's easy to check if you're right. Yeah, like, so here's y equals 2 to the x, right? So if I could have written this as a horizontal shift. It's just that it would have been, here's my 3, here's a y value of 3 on the original. I would have to figure out how far that shifted to the left, and I could write it as a horizontal shift. That looks like, I don't know, 1 point something, right? I could also do 2 to the x plus 1 point, whatever that number is, 7 or something. So you could take your original graph. Oh, actually, is that a constant distance? I don't think it's a constant distance. I don't think you can do that.
If it's a shrink, then it's going to change.
Yeah. Yeah, if these distances were all constant, then you would do a horizontal shift. Looking at those distances, you'd go, yeah, these are getting further apart as you get higher. So it's not a horizontal shift. So we could rule that out. To write it as either? Yes. Yes.
It can be constant though, because both of the
I think it is. I think these actually are a constant distance. If I keep drawing these, they are pretty constant, aren't they? Right? Okay, I changed my mind. You can do it. Let's do this could be 2 times x plus 1.7-ish, right? Because, and why are those two equivalent? Let me do it on a different page here. 3 times 2 to the x versus 2 to the x plus 1.7. Well, remember that rule that we learned a while back that if you're multiplying like bases, you can add the exponents? So I'm adding exponents here, right? So maybe I could write this like this. But then 2 to the 1.7 has got to be close to 3. It should be, whatever that is, should be exactly 3, but I just estimated it. 2 to the 1.7, 3.24, yeah. So this number is like 3. I completely estimated it, so it's a little bit off. But so I have a 3 over here. So these two formulas are equivalent. I estimated it from the picture. I drew 2 to the x, and then I looked at how far apart various points were horizontally. Is it exactly 1.5? I don't know.
Yeah. It's 2 times.
1.5, let's see. 2 to the 1.5. No, it's not 1.5. 1.6 is really close, yeah.
Try 1.5.
So anyways. Okay, so we can figure out formulas of standard exponentials, just b to the x. We can do transformations of something of the form b to the x. And I believe in your homework, I always tell you what the parent is, so it's easier to identify the transformation. Much easier. I should do that from now on. These are transformations of y equals 2 to the x. That would make it easier, right? That's usually given. Okay, an irrational number that we symbolize by the letter e appears as the base in many applied exponential functions. Like when you're out in the real world and you're using exponential functions, this number just keeps popping up. It's irrational, which means it has a decimal expansion that goes on forever and never repeats, kind of like pi. And we call it the number e, and it's defined as the value that 1 plus 1 over n to the n approaches as n gets larger and larger. So this is exponential, right? I've got a variable in the exponent. This is an exponential expression. So I'm going to put that in my calculator, that expression in y equals. I have to use x instead of n because I don't have an n button. So I'm going to do 1 plus 1 over x to the x. And I'm going to use my table to fill this stuff in. All right, so when x is 10, y is 2.5937. And when x is 100, I get 2.7048. And 1,000, I get 2.7169. 10,000, 2.7181. And I could keep putting in bigger and bigger numbers. Like I could put in a million. 2.7183. And so I could barely change it all from 10,000 to 1 million. If I put in 100 million, 2.7183 again, right? So it's rounding. These decimals actually keep going on and on forever. So the value e is approximately 2.7183. So it's approximate because as soon as you chop off a decimal, you've rounded it. But it appears as the base of applied exponential functions so frequently that we call it the natural base because it happens naturally all the time. And the function e to the x is called the natural exponential function. And here's a picture of it, e to the x graphed. So we have, this is the point 0, 1, right? For any base, the y-intercept is going to be 1. And then 1 comma this number here would be 2.7183. Because that's your multiplier. And then you'd have 2, this would be 2 comma e squared, whatever e squared is. All right, so take a few minutes now. We'll have you do a little practice in your groups to match each of these functions, each of these transformations of the natural exponential to its graph. So they all have the natural exponential graphed in the light color, the thin line, and then the bold line is a transformation. So try to match each transformation to its graph.